Alright, so we are now going to start a new section titled Another Counting Principle. Another because we already have come across one counting principle in the 5th section, which enabled us to prove this formula. If you remember, this is the formula that calculates the number of elements in this product Hk of two finite subgroups H and K of some group, and that's where we saw one counting principle. Now here we are going to see another counting principle, and this starts by defining a relation, a binary relation in any group called conjugacy. So let's see what it is. So let's start with the definition. Let G be a group and A and B be elements in G. We say that B is a conjugate of A in G if there exists an element C in G such that B is equal to C inverse AC. So that means we have a group G in that, say, two elements A and B are given. Then we say that B is a conjugate of A in G if for some element C in G this equation is true, that is B is equal to C inverse AC. We express this by writing this symbol. That is, when B is conjugate to A or B is a conjugate of A, then we write that, we express that fact by writing that symbol. And this relation in G is called conjugacy, and the name of the relation itself is called conjugacy. You can clearly see that this is a binary relation in G, and that means it relates two elements of G. Any two elements, for any given pair of elements, one of them may be a conjugate of the other, may not be a conjugate of the other, but the relation is a binary relation, so it's a relation defined on G. Now it turns out that this relation is actually an equivalence relation, which is why it becomes important. So that is this lemma, first lemma of this section, first result of this section. And the statement is just this: conjugacy is an equivalence relation. So in the context of this discussion, we understand what the statement is. In general, if we just simply say conjugacy, then that may not mean just this thing. In the context of our discussion and then in the context of group theory, it means this particular relation. So the proof is really very straightforward. Let G be any group. So to show that this is an equivalence relation, we have to show that it is reflexive, symmetric and transitive, usual things. So because for transitivity we will need 3 elements, so let's take any 3 elements in G. Let A, B and C belong to G. Number 1, since A is equal to E inverse AE, you can see clearly why that is so. E is the identity of in G, of course. So A is related to A. Thus, the relation conjugacy is reflexive. Note that reflexivity demands that every element be related to itself, that every element part is important. Here, since A is an arbitrary element of G, so A being related to itself also means that this is true for all A belonging to G. So that's why we are concluding thus conjugacy is reflexive. Next, let us prove symmetry. Let A be related to B. That means B is a conjugate of A. Then there exists some element C in G such that by definition B is equal to C inverse AC, but then what can you write from this equation? If you multiply on both sides by C from the left and by C inverse from the right, then you get this CB C inverse, which itself can also be written like this: C inverse inverse B C inverse. Now this final equation tells us that just like B is a conjugate of A is also a conjugate of B. Note one thing carefully, that we had to write this in place of C in order to have the form that we have in the actual definition of conjugacy. Thus, A is a conjugate of B, i.e. B is related to A. So whenever A is related to B, then B is also related to A. Hence, conjugacy is symmetric. And then the third one is transitivity. So for that, let A be related to B and B be related to O. See, I cannot take C here because I have already chosen C to be an element here. So let me change this to what? Let me keep C, but let me make it C prime, because this C prime may not be C, that is something else. Yeah, now it's okay. Then B is equal to B and E also. Let me take U and V. U inverse AU and C is equal to V inverse B V for some elements U and V belonging to G. Okay. This implies C equal to V inverse B V. Now, but in place of B, we can write U inverse AU. V. So you have V inverse U inverse A U V. We are being able to use brackets in any way we want because we have the associative law. Now V inverse U inverse, we already know, is the inverse of UV. So again the desired form has appeared. Something inverse times A times that thing. Since UV is again an element in G, we have this. So our relation is also transitive. Thus, conjugacy is transitive. So that's it. We have shown that it is both, it is reflexive and symmetric and also transitive. Hence, conjugacy is an equivalence relation on G, and that completes the proof of this lemma. Now we know that whenever we have an equivalence relation on a set, then there are equivalence classes which taken together form a partition of the set into mutually disjoint non-empty subsets, the union of all of which is the entire set. So let us now see what that thing becomes here in this, for this particular equivalence relation. for any element A in G, we have the equivalence class containing A. We know that every element of G will belong to precisely one equivalence class. So that is the class we are talking about here. And that class we already know is denoted by this symbol C of A, and this is not just for this equivalence relation, but in general for any equivalence relation. C of A, or sometimes we write like this also, class of A. Okay, so C of A, that notation is being used here. So this CA by definition is nothing but the set of those elements in G that are related to X. And it does not really matter whether you write A tilde X or X tilde A due to symmetry of the relation. Okay, now note one thing, that this is how far we can go if we do not know whether G is a finite group or not. But if G is finite, then it becomes really interesting, because in that case all the equivalence classes of in G also become finite, because they are after all subsets of G. So now let G be finite, then each equivalence class, but I forgot to say something else is also there. These equivalence classes have special names. This equivalence class is usually called the conjugate class of A, or sometimes the conjugacy class of A. In this text, conjugate class, that term is being used. Okay, so now let us consider that the group is finite. Now let G be finite. Then each conjugate class is also finite. Each conjugate class CA is finite, so the number of elements in each such CA will be an integer, and in fact it will be a positive integer, because no conjugate class for an equivalence relation, no equivalence class for an equivalence relation is empty. Every equivalence class is non-empty. So that number of elements is now what we are interested in. So let's give it a name. Let CA have this many elements. Small c suffix a, number of elements. Now we will be interested in finding out this CA by some means in terms of something else, and that's where this next result comes in. It's a theorem. It is so important that it's not a lemma anymore, it's a theorem, and this is theorem 211.1. I have kept some space for something. Let me first state the theorem and then we will see why we need this space. Perhaps I need a little more space because I need two more items here. Let me write the theorem here. Why am I not writing whatever should appear here now itself? You will realize now. If G is a finite group, then CA G is a finite group and A is an element in G, then there is a formula relating CA with something that we already know. This NA is the normalizer of the element A in the group G. In other words, the number of elements in the conjugate class C of A is the index of the normalizer of A in G. Now we already know what the normalizer of an element in a group is, but because that has appeared not in any portion of the text, not in any section as a definition, but has appeared in one of the previous exercises. So that's why the author has decided to define it properly, rigorously here, formally. So that's why this place is kept for this definition. Let G be a group and A be an element in G. the normalizer of A in G denoted NA, or if you want to really express the fact that this is the normalizer of A in G, sometimes we also write that G as a suffix. Here, however, that has not been done, perhaps because we do not need that. So we are just simply writing NA is defined as NA equal to the set of those elements in G that commute with A. All the elements in G that commute with the element A form the normalizer of A in G. Now, there is a result which is also something we have already proved. In fact, the next result is what we proved in that exercise where we came across the notion of normalizer for the first time. So that result is a lemma This is lemma 211. It will be 2 because we have already seen another lemma, which is that NA is a subgroup of G. Now we have already proved this, and that's why I am not writing anything more on that. In the text, however, this has been proved. And if you want to recall what that exercise was where we proved this, this is the exercise. Exercise 13 at the end of section 2.5. That is, you go back to the 5th section. There you have that this section is titled A Counting Principle. After that you see the exercises there. The 13th one is this one. And that's why it makes sense to say the index of the normalizer of the element in the group. And when you calculate this thing, it turns out that that is equal to the number of elements in the conjugate class of A. So we are now going to prove this theorem. So let's see the proof. The idea of the proof is that two elements in G that come from the same right coset of the normalizer give us the same conjugate of A, and also conversely. This may sound very confusing. Let's see what I mean by that. Okay, let us first consider two elements. X and Y belong to G. Assume that X and Y belong to the same right coset of NA in G. So we already know precisely the right coset of NA in G where we have the element y. What is that right coset? We know that y belongs to this right coset NAY. And what is the reason for that? The reason is NA being a subgroup has the identity element, and you know the structure of every element in NAY. It is any element in NA times y. So you take E times y, you get y. So our assumption is that X also belongs to this right coset. And keep in mind that because the right cosets form a partition of the group, so y already belongs to this right coset, so it cannot belong to any other right coset. So that's why this is the only unique right coset containing y. So our assumption now says that X also belongs to this. Which implies X also belongs to NAY. Thus, X is equal to NY for some N belonging to NA. Now our aim is to calculate the conjugate of A given by X. In other words, we are now going to consider the element X inverse AX. That's what we mean by the element, the conjugate of A given by the element X. Then X inverse AX, let's now consider this element. Since we have something for X, let's substitute that and see what we get. NY inverse A NY. So this becomes Y inverse N inverse A N Y. Now look at this condition. N belongs to NA, so N belongs to the normalizer of A, so N should commute with A. So in place of AN we can write NA, we can switch the order. So N inverse and N, they cancel out, they vanish, and we are left with Y inverse A Y. So whenever X and Y are coming from the same right coset of the normalizer, then the conjugates of A that they produce are the same. They produce a unique conjugate of A. Now conversely, so X and Y still remain X and Y. Under this assumption, we proved this. Now we are going for the converse. Conversely, assume, or okay, we may confuse ourselves here with the things we have here. So let me take new elements. Conversely, assume what should I take? Do we have any u, v here? No, we had u and v's previously, right? Okay. Conversely, assume that u and v belong to G such that u inverse AU is equal to V inverse A V. Okay. Then what do we get? If we multiply on both sides by u from the left, then this u inverse and u will cancel out, and we will be left with AU equal to u V inverse A V. Now you multiply on both sides by V inverse from the right. That gives you AUV inverse equal to UV inverse A, because this V and V inverse, they will cancel each other. Now you look at this. This equation clearly shows that UV inverse commutes with A. So UV inverse must belong to the normalizer of A. That is, UV inverse is equal to some element nu for some nu belonging to the normalizer of A. Then what is U? U then becomes nu V. Now because nu belongs to this element belongs to the right coset NAV of NA in G. But since U belongs to NAU, U belongs to this right coset that we are getting from this calculation, but U already also belongs to this right coset, which we already know, and we know that two right cosets that are distinct are disjoint. So if these two are distinct, then they should be disjoint, but that is not possible because we have already obtained one element in their intersection. So they cannot be distinct. So we must have this. And if you look here carefully, this one, you look at this one and this one, then you can apply the same argument and conclude here itself that NAX is equal to NAY. So what we have shown is this, that if you have two elements X and Y in G, then NAX is equal to NAY if and only if X inverse AX is equal to Y inverse AY. This is what we have been able to show. Now we are going to use this fact to define a function. We can do it here itself, no? Or let me do it there, because another paragraph. Now define a function f from the conjugate class of A into G slash NA, where this notation may be confusing, but it is something that is actually used, where G slash NA is the set of all right cosets of n in A. I mean the set of all right cosets of NA in G. Why I said that this notation may be confusing is because the same notation is also in general used to denote the factor group. When you take the factor group of a group by a normal subgroup. Here, however, NA is not necessarily normal, and we do not have anything to do with normality here. By this notation, we just mean the set of all right cosets. Okay, now let's define the function y. So, if you are going to take any element from CA, it should be a conjugate of A, and that conjugate is going to look like this: X inverse AX. That's how a general conjugate of A looks like. Its F image, I am defining it to be this right coset of NA in G. Now we need to first of all prove that this function is well defined. For any alpha and beta belonging to G, let alpha inverse A alpha be equal to beta inverse A beta, so that we are considering only one element, a unique element in CA, but it has two different representations in this form, in this particular form. But depending on the representation itself, we will have then two different images. Now, if we are unable to prove that the images actually are also the same, then the function will not be well defined. In fact, it will not be a function at all. So let us now see. But then because of this thing, because of this implying that line above, NA alpha is equal to NA beta, i.e. you have this. So if you have a single input but two different representations of that single input, then it does not matter which one you use to generate your output. You get a single output itself. So F is well defined. Also, if you have two elements gamma and delta in G such that gamma inverse A gamma F is equal to delta inverse A delta F, then if the outputs are equal, then this is nothing but Na gamma and this is nothing but Na delta, which implies, again due to that equivalence, so if inputs are equal, then outputs are equal. That shows that the function is well defined. But if the converse is also true, that when outputs are equal, then so are the inputs, that means the function is one-to-one, it's injective. And something else is almost obvious, that our f is surjective. Why? Because you choose any element in this second set, it looks like this, but then what should be its inverse image? Just simply this x inverse Ax. That is, f is bijective. So f is a bijection between this conjugate class and this set of all distinct right cosets of Na in G. But that is what is the number of this, what is that number called? The number of elements in this set. That is nothing but the index of Na in G. And we have a formula for calculating that number also. It is the order of G divided by the order of Na. Precisely that many distinct right cosets Na will have in G. Hence, Ca, which is the number of elements in the conjugate class or the order of the conjugate class, Ca is equal to the order of this set, which is nothing but the index of Na in G, and that is equal to this quotient. And this completes the proof of our theorem. So this theorem enables us to calculate the size of each such conjugate class in terms of that is as the index of the normalizer of the element whose conjugate class we are considering. Now, a consequence of this is this corollary. If G is a finite group, then the order of G is equal to the sum of such quotients. Where the sum runs over a set of elements A in G which has exactly one element from each conjugate class. Let us see how this now can be derived from this result. Since the conjugate classes form a partition of G, and also because G is finite, that of course is understood, it's given that it's finite, the order of G is equal to the summation of such sizes of the conjugate classes, where the sum, here also the same thing, the sum runs over a set of elements with one element from each conjugate class. The previous theorem now completes the proof, because each such CA is just this. Now let us see what has gone on here. So basically what we are saying here is very easy. Once you have that main theorem, the rest is very easy. The situation is like this. G is a finite group, okay, and our conjugacy equivalence relation partitions G into distinct equivalence classes, which we are calling the conjugate classes. Now there are elements in each conjugate class, at least one element, because they form a partition, and as such each conjugate class is a non-empty subset of G. So naturally, if we want to calculate the order of G, then we would have to take the sum of the sizes of all the conjugate classes. That's what it will be. Say you have a house in which or say you have an apartment complex in which there are apartments. In each apartment there are some inhabitants. They may not be the same, say this apartment may have one number of people living there, this apartment may have another number of people living there. So in order to calculate the total number of people living in the complex, you have to take the sum of each individual apartment's size, strength. So that's why we say that the sum varies over a set of elements A in G, which has exactly one element from each conjugate class. Each apartment has some representative, say someone A1. Here you have A2. Here you have A3, A4, A5, A6, A7. So for this particular situation, this sum is this CAI, where I varies from 1 through 7. So that set of elements we are talking about here is this set, which has exactly one element from each conjugate class. And now you know what each CA is. Each CA is the index of the normalizer of that element. So that's why we have this formula. And this formula it has a name. It's called the class equation of the group. And it's a very powerful and useful equation. It has many non-trivial consequences which will tell us many things about finite groups. Many more things, more than what we have got so far. The equation in the corollary above is usually called the class equation of the group G. And clearly the class equation makes sense only when G is finite. Now, before we end things for tonight, let us see this whole thing in a specific group. You look at S3 in the non-abelian group S3, the conjugate classes are these, which one can verify. One conjugate class is the one that contains the identity permutation, which consists of that itself. Another conjugate class is one which contains the two cycle, the transposition 1, 2, and this consists of all the two cycles. And there is another one which contains the 3 cycle, and it consists of all the 3 cycles, of which there are only 2 in S3, 1, 2, 3 and 1, 3, 2. Now simultaneously, if you look at the normalizers of these elements that we have considered here, E 1, 2 and 1, 2, 3, then you get this. The normalizer of E, of course, is S3 because every element of S3 commutes with the identity element. In fact, this is the case in any group. Then the normalizer of the element 1, 2, it turns out it has the identity element and 1, 2, and that's it. Now there are some things, I am just simply mentioning the facts, but it's definitely left to you to verify that these are really the way they should be. So you have to go through the calculations, but there are ways of simplifying the calculation. Let me first write the other normalizer, another one I should write, and then I will tell you something about how one can make sure that these calculations are true. Okay, now when you are going to calculate conjugate classes, keep in mind that they form a partition of G in general. In this case, they are going to form a partition of S3. So you know what the elements of S3 are, right? There are these 6 permutations. Now, when you form a conjugate of the element E, you take any element from the S3, say that element is X, then the conjugate of E given by that element is just simply this, X inverse EX, which you can clearly see is going to give you E. So, the only conjugate of E, not just in this group, in fact in any group, is E itself. So this conjugate class is going to contain the sole element E. Fine. So that this element has formed one conjugate class. Then you look for the conjugate class of 1, 2. Because a conjugate class is after all an equivalence class. So the conjugate class of 1, 2 is going to contain 1, 2. No doubt about that. That is because 1, 2 is related to 1, 2 because our relation is reflexive. It's an equivalence relation. So you know that this is there. And then you form the other conjugates. Say you calculate this and see what it becomes. If you do that for all the possible elements, you will see that you get these 2 others, and that's it. So these 3 form another conjugate class. Now because conjugate classes, distinct conjugate classes are disjoint, the already considered elements which have already formed their conjugate classes will not appear in the new next conjugate class, whatever else may be there. So next you calculate the conjugate class of this. This is automatically there, and you will then see that this also is there. You have to form conjugates of this by again some elements, and you will see that this forms, these 2 form another conjugate class. So that's how you have the conjugate classes, and once you have run out of elements, that's it. You have the full partition of S3. And now when you calculate the normalizers, normalizer of E is S3. I have already just now said why, because every element of S3 commutes with E. Normalizer of 1, 2 is going to definitely have E and 1, 2 because both of them commute with 1, 2. But you also keep in mind that any normalizer is a subgroup. So if it already has 2 elements, then if it must have more than 2, it can then have either 3 elements or 6 elements, because we have Lagrange's theorem also. So keeping those things in mind, you will see that this is in fact the normalizer of 1, 2, and that's how you can also verify this. And now if you want to verify, if you want to see the class equation being true in this case, so you calculate the sizes. What is CE? CE is the size of the class equation of E, 1. Now 1 can be written as what? 6 divided by 6. 6 is of course the order of S3, and the 6 in the denominator is the order of the normalizer of E, which is also S3. Next, what is the size of the class, conjugate class of 1, 2? 1, 2, 3. 3 can be written as 6 over 2. So 6, the numerator is always the same. In the denominator, you see what is the order of this normalizer of 1, 2, 2. So that's why this. And finally, the conjugate class size of this 3 cycle, 3. No, I think, no. What I said now is wrong. It is 2 because this is the conjugate class. So this is 6 over 3 divided by order of the normalizer of this. So you see that we have in fact verified the class equation. In fact, we actually, the way we have written things, we have verified that theorem. But now you know that you can write the class equation from here for S3, and that looks like this. That is equal to 1 plus 3 plus 2. These are the conjugate class sizes. This C is C12, C12, 3. But that now is nothing but this. And this is that sum that we see in the corollary, in the statement. So that's how we have verified it for S3, and we already know, we have proved it today, that in general for any finite group we have this fact. Now in the next group theory update, we are going to see how one can use the class equation along with some other group theoretic techniques to say many things about finite groups. And the major thing among them is this: if G is a finite group whose order is the power of f prime, and say here n is greater than 0, that is G is non-trivial, G has at least 2 elements, then the center of G is non-trivial. That is, if this is the case, then the center of G must have at least one element different from the identity element. So, for example, if you have, say, a group whose order is, say, 17 square, it has quite a few elements, but we would automatically know that its center would have something other than E. So there is a non-identity central element in all such groups. So we will see these things. Okay, and let me just end the video here itself for tonight. And our next upload is, of course, this coming Friday, and on Friday let's go back to field theory. And until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.